So this one I like a lot. By the way, I heard the question about WebAssign. Yeah, so if I ever am behind on posting stuff on WebAssign, just remind me. Not everybody's on there, so yeah, pretty good ears. You know, teachers, we have that happen to us. Eyes in the back of our head and stuff. 70 is a question that if I don't get a question on it, I get worried. So they show you this kind of nifty thing. All right. And then right below that, they've done something interesting to that. And let me just show you what they did, because you have to do the same thing to a different polynomial that they give you. And if you don't see what the hell they did to get from P of X to Q of X that they have there, you know, you have to be able to do it. Right? Obviously, the last problem in the thing, it's after the discovery, discussion, writing thing. If you haven't noticed, those are normally a little bit harder. If that's the only one you're having trouble with, you're doing pretty damn good. All right? So how the hell did they get from there to what Q of X is? What the hell? And Q of X looks like this. Russian nesting doll here. Blah, blah, blah. 1, 2, 3. I like it. I like it a lot. So you can see all the kind of coefficients in there, right? But how in the world did they get from here to there? If you work from the end up, it's actually easier. All right, so let me show you what they did, and then you can do the same thing to the one you have to do it to. So 5 plus, I can take an x out of all this here, right? And then what would I be left with?
3x3 5x squared.
I'm just taking an x out, so all the x, it's all lost 1x, right?
Yeah.
And then inside here, I can take an x out of this stuff. You guys see now, this is how it gets there, right? You guys see that? Now again, I mean, how often would you ever use this? Even less often than the other math that we talk about, right? This is not very often used, but actually it's a neat trick that's related to a lot of stuff that you do with computer programming, for example. Just to make it quicker for the computer to do stuff. If you can save a second here and you do it 80 billion times, that's a lot of time saved, right? So then you end up, you keep doing like this, you'll get here. Now watch this. If I wanted to know what's P of 2, if I do it from here, I have to do 2 to the 4th and then multiply that by 3 and so forth. Now watch, and Q and P are the same damn thing. And I hate that they gave them different letters, but they're the same thing, right? It's just reorganized. How do we do Q of 2? Yeah, just plug it in. So this would be 6 minus 5 is 1. Times 2 is 2. Plus 1 is 3. Times 2 is 6. I mean, do you see how simple that is to do now?
No.
Damn! Alright, so if you plug a 2 in, what do you get? 6 minus 5 is 1. What's x again?
1. 2.
What's x again? All right. So 3 times 2 is 6, minus 5 is 1, times 2 is 2, plus 1 is 3, times 2 is 6. X is 2. So it actually is easier to do. You guys still don't believe me. All right. Just understand what's going on. 3 times 2 minus 5 times 2. It's harder if I actually have to write the damn thing out. 2 minus 3 times 2 plus 5. Now let's hear some. 6 minus 5 is 1. Times 2 is 2. Plus 1 is 3. It's crazy. Times 2 is, oh my gosh. Minus 3 is
3.
Times 2 is, plus 5 is 11. Now if you do this, 2 to the 4th times 3, and then 2 cubed times 5, you'll get the same damn thing eventually. So it's just a realization that we can reorganize the problem that we're given into an easier thing to work with. This is one thing you would never even probably think of doing this. You're like, why the hell would I ever think of doing this? But it actually makes it really quick. Anyway. Now obviously, doing exactly this wouldn't help a computer out, because a computer could eat this, chomp this up all day. But there are nifty little things you can do with other things computer related. So then they give you your own. They give you R of X, and you have to write that in the same way. Once you see this, then it's relatively easy to see. Start at the end, that's the thing you got to realize. That's how you do this process. Okay, cool. That's all I'll say about that. It's plenty. Not something I'm going to throw at you at a test or something. All right. You're all looking at me like, you're a math teacher. We don't trust you. I'm not.
I just don't understand how did we took the 5 off the end?
No, we didn't. And the 5 is still there.
Okay.
Took an x out of all this. Right? So all this is 1 less x. Then inside here, out of these, I can take another x out, right? So the first thing I did was out of all this, I can take an x. And the plus 5 is just sitting there. And then, all right, I do that. And then out of all these, I can take an x. And then out of all these, oops, why did I leave it off? Yeah, that's fine. And then out of these two, I can take another x. And so I end up here. All right, just try it. If you haven't tried it yet, what can I tell you? Give it a try. It's not as hard as it looks at first. Yeah. Oh, you good?
Yeah.
Any other questions from homework? All right. Really? All right. I'm an optimistic fool. I'll take that as a good thing. You guys should be, by tomorrow, you should definitely be almost done with section 3.4. That's why the quiz tomorrow is 3.3 and 3.4. Right? And it's remarkable. If you do the homework, you do so much better on the quiz. It's crazy how it works. Yeah. Yeah.
64 feet. 331.
Which one? Oh, 3.1. Oh. So back in section 3.1, 64B. Oh, okay. 64 was this beautiful one with the really nice first coefficient. Y represents the horizontal distance traveled, right? That's what they tell us. Blah, blah, blah.
Was that throwing the ball in the air?
Well, X is the distance in feet that the ball has traveled. Say again? Yeah. Throwing the ball across the field. X is the distance. X is the horizontal distance. Alright, cool. So then they ask you, when this thing hits the ground, how far has it traveled? So Y is the height of this thing. So when this thing hits the ground, I'm going to make Y equal to 0. And then solve from there. Yeah, it's basically finding the x-intercepts. You'll get 1, now since it started at time equals 0, here's a little dude, and he's throwing the ball, it's already 5 feet up in the air. So maybe he's not such a little dude. Yeah. So the ball itself is 5 feet up in the air, so maybe he's holding it over his head, and he throws it. So that's going to be our answer there. Mathematics is going to find us that answer too. Right? Mathematically, it doesn't look at that as it started here. Mathematically, it says, well, you can go both directions. You know, negative time. Yay. So you got to just throw that one out, of course, right? Like you always have to. But the physical problem. Don't tell me it's going to take negative 8 feet of wood to make your shed. What the hell's that shit? Right, so just throw that one out. You got a quadratic, you're going to get 2 answers. And how do you solve? If you make this 0, how do you solve? How do you solve that? How do you solve this here?
Is that x squared goes into negative 32?
Yeah, it's a square in the 20 and a square in the x. I mean, this is that ugly coefficient they gave us.
Oh,
Yeah, quadratic formula. Don't let the number tell you what the hell to do. This is an ugly looking number. Where's the number? Who cares? When you have something in this form, how do I set it equal to 0? How do I find the answers? Quadratic formula, right? We're the humans here. We don't let the numbers tell us what to do. We're like, screw you. You're ugly, but it's just an x squared thing. I use quadratic formula to find the intercepts. I think that number's freaking us all out about this problem. It's partially why they gave it to you. He said, the number shouldn't freak you out anymore. All right. Processes don't care about what numbers are in there. We do a little bit. We're human. We care a little bit, but... All right. Anything else from homework? Say again?
Like, I did the problem differently. I suddenly wrote more about making
Oh, that's part A. I'm talking about part B.
Oh,
Yeah, this is part B. The question was on part B. Yeah, how far will it have traveled once it hits the ground? That's part B. Yes?
Can you do number 80 on 3, 4?
3, 4, number 80? Okay, that's actually a decent little review problem. It's got a this has actually got a lot of this.
Like specific question, like they asked you like to find the upper and the lower bound, but not giving you like the ones that actually like alternate or give positive numbers. So that's what my question was.
No, they don't tell you that. They say whenever appropriate.
I'll go no.
Yeah, whenever appropriate, use the rational zero sum. So when is it appropriate to use bounds? If I'm just doing a problem like this, if I divide by something that doesn't work, I can step back and say, well, is it all positive or are they alternating, right? So be real careful. To find an upper bound, what exactly would I do? Or how would I get there? Starting with what kind of thing, though? I'd have to divide by a positive. So if I divide by a positive, and the answer ends up all positive, that's an upper bound. If I divide by a negative here, and the answer turns out alternating, that's a lower bound.
So in order to find that, you just keep plugging numbers.
Yeah, but that's not your point here. You just use the idea of bounds if it happens to come up to help you. Right? You don't have to focus on that. Right? But what would Descartes say?
They're all the same right now.
He would say, I am dead, leave me alone.
There's
Walking Descartes edition.
no sign changes.
Yeah, there's no sign changes in P of X.
There's no positive roots.
Yeah, there's 0 possible positive rational roots. Neat. Yes, sir.
So in that case, the upper bound would be 0.
No, it's just 0. Well, I see what you mean. Yes. Sure. That's another way to say the same thing. There's no possible positive rational roots, so bound is 0. Sure. I like it. How else? What's one more thing Descartes might help me with? What else do I have to look at for that? P of negative x. And all that would be all the odd things change sign. So how many possible negative roots are there? You can do this.
4.
Yeah, that'd be 1, 2, 3, 4. 4 or 2 or 0. I like it. 4, 2, or 0 negative. Possible negative. Make the grammar all get rational roots. Okay. And then you make your list. What's really nice on this one is the list is going to be relatively short. Right? But how exactly do I make my list here?
Expect coefficient. Then back to the last. Coefficient.
List of possible rational roots. It takes too long to make words. Rah. So you do plus or minus. What goes on top?
4, 1, 2, 4.
I like it. 1, 2, 4, or 4, 2, 1, or however you want to order the factors of 4. Divided by
plus or minus 1.
plus or minus 1, 2.
Can't you already come out the...
Yeah, the plus or minus 1. Yeah, exactly. Good. So we've already done Descartes, but this would be like I would actually ask you this question first. And then Descartes would say you can throw out all the positive ones, so you know it's going to be a bunch of negative. So what are the possibilities here? 1, 2, 4, right? And then 1 over 2. 2 over 2 you've already got. And 4 over 2 you've already got. So there's your whole list. There's only 4 possible things. That kicks ass. Cool. Yes.
And due to the second where it says there could be 4 possible rational roots, technically all of them could work.
Yeah, they all could possibly work. Yeah. The minute one of them doesn't work, then you know you only have 2 possible, right? Which means the other ones would be either complex or irrational. All right. Is that cool? Is that understood? I should use that word instead. You're like, I understand it or something. All right. Sure. Yeah.
100 on 3.4.
Dimensions of a lot. Huge parcels of land. Let's see. Oh, they already give you the little picture. So evil. So they say this parcel land has an area of 5,000 square feet. And they give you the picture already. They tell you the diagonal is 10 more than the length. Yeah. And this has got an area of 5,000 square feet. What are the dimensions of the land? Round to the nearest foot. So how the hell would you do that? What are you missing to tie what you know with what they tell you here? What are you missing? I'm missing this width here, right? All right. So this tells me that x times y is 5,000. Is that cool? But I can't deal with 2 variables. I'm not in multivariable math. Yeah. What relates these sides here? Yeah, I think somebody just said it. Pythagorean theorem. I love it. And this is where we kind of give up on the problem. But this one's not as bad as it could be. I mean, what would Pythagorean theorem say? X plus 10 squared
Plus x squared.
equals, because that's the hypotenuse here, right?
X squared plus x squared.
X squared plus y squared. Now solve for y. Right? And you can't have a plus or minus here because y is a length. So you can throw the negative one out. Yep. And the beautiful thing that happens here, of course, is the x squares cancel. So you get y equals radical this. And you throw that bad boy in there. Or, alternately, maybe a little bit better, what's y here?
5,000.
I think that's what somebody was trying to tell me, but I was working on the other one. And then now I can throw that in there. And you should know what form to expect the problem to come out in considering what section we're in, right? It's going to be some kind of a x cubed plus x squared plus x, kind of thing that you have to factor. Is that enough to get you started on that problem? All right. All right. Anything else from homework? You guys doing all right? You guys bummed out about the quiz? Don't forget you can make corrections to the quiz.
I did the homework and I still was a little bit lost. But
One of them came right out of the homework.
yeah.
Not necessarily exactly one that you were assigned, but it's right out of the homework. So I don't know, when you do homework, the most important thing to get out of homework is the processes involved in answering the questions. I almost don't care if you get the right answer to anything in the homework. That's a weird thing for a math teacher to say, but just deal with it. Right now, what's most important is, do you understand the process of what to do? That is the most important thing right now. When you get into a job where you might have to use math every now and again, then you better get the right freaking answer too, or else you might not have that job for very long. But you ain't there yet. You ain't making money in here that I know of. Right? So don't depend on the answer so much. And nice, the right answer is nice. It's like a little frosting on the cake, but the cake is the freaking process, right? All right. All right, so let's do this. We're going to get into section 3.7. Actually, I'm sorry. We need to finish out something from 3.5, and then I want to remind you that 3.6 is basically something we've already done. And somehow, let's see how much time we got left. Just to remind you guys, too, the test is happening Thursday. Good. So that I have time to grade tomorrow's quiz, and hopefully we'll have time to get actually through all of chapter 3. That should be good. One last thing from section 3.5. That was a section all about complex numbers. So a little review. Help me out here. Do these two problems real quick. Simplify these. Get it or you don't situation here. Remember, what's I again?
-1. Or the square root.
Square root of -1. I like it. So what do I be? I be the square root of -1. Grammar goes out the window when I have I's here. What is I? What is I all about? And of course, the only thing you got to be careful about here is the same old thing that's been killing people ever since math day 1, is that minus signs always find a way to hurt us. 4 minus 7. -2 minus 6. All right. And for some reason, sometimes people have this problem become a multiplication problem. They start foiling it. This is a subtraction problem, right? That would be like math Jesus, taking subtraction and making it into a multiplication. And then we're like, where's the 1, dude? If that was sacrilegious, that's too damn. So that's what you get there. That's a subtraction problem. It can't become multiplication. Now this is totally multiplication. Beautiful. So you should realize something interesting is going to happen. You have two very, very complex numbers with imaginary parts to them. But when I multiply these, here I get... Yeah, good. You get 16i squared. Let me just show all the little steps here. Minus 4i plus 4i. So the middle terms cancel, like I expected. And then 1 times -1 is minus 1. And of course, I squared is...
-1.
So negative 16 minus 1 is... Yeah, so two very imaginary part numbers multiplied and it becomes purely real. That's neat. Well, we've seen that before. We've seen that kind of thing before. Right? Remind me, how would I do... Partial recall. How would I do... Let's see. This is a recall, so if you guys... Like, I've never seen that before. It's no good.
Multiply by the
Beautiful, right? So here I would multiply by...
square root
On the top and bottom. And who cares what that answer is? It's old news. But now if I had something like 1 over 4i minus 1, multiplied by the conjugate. And why is it the exact same idea? Because I is just a radical. So why shouldn't it work like the other radicals do? And it totally does. You guys kind of with me. So I multiply by the complex conjugate. Whoa.
4i plus
1. I'll do 4i plus 1, right, over negative 17. So I can write that as, you can leave it like that, or you can write it as negative 4/17 I minus 1/17. So it's a plus bi. It's kind of like backwards, but who cares?
So I say, do you care if I is in the front or back?
Doesn't matter.
I'm supposed to write it back.
Because it's sort of like mx plus b. It's kind of arbitrary to put that in the front, but it's even more free than that. It doesn't matter to me. All right, how are we doing so far? This should be a walk down memory lane. We should all be very familiar. You've seen complex numbers before. So here's the semi-new stuff, mixing with this complex stuff. So one last thing in section 3.6. Section 3.6 is section 3.4. Section 3.6 is section 3.4 with the addition of complex numbers being part of the answers. Right? So let me give you guys a problem to work on for a second. If I give you this, factor that over the reals. So when I say over the reals, that means you can stop when you get to the point where the next step would be complex. Hopefully, now this is a semi-new thing, so can you factor that using a process you could before you got here? No, right? Because it's cube up there, right? It's not gonna, and there's not 4 terms, you can't group, there's no nice way to do that, but we know now the tool to use when it's not something recognizable. What do you use?
Quadratic.
Can't use quadratic because it's cubic.
Synthetic.
Synthetic. Kick ass. All right, do it. I'll wait. This is there's only one real answer to this. So if you're lucky or somebody got it pretty well, what's your little list look like that you're going to try?
1, 2, 4.
Even better than the last one. There's just a 1 out front. That kicks ass. So there's like 6 numbers to try. So most people try 1 first. But who got something that works?
2.
-2.
Negative 2. So see, how do I set this up?
1, 0.
Good, because I'm missing an x squared, right? So if you don't put a 0 there, you'll be doing this all day. You go a little insane. Just don't go postal. And then if we do this, let's see if this works. 1, -2, -2, 4, 2, -4, 0. Yeah! So what have we factored this as so far?
X plus 2.
Good. X plus 2. Sorry, go ahead. X squared.
Minus 2x squared plus 2.
Good. And I call that factored because there's no remainder, so it actually did go in even. So this is a factored form of this polynomial. Let me stop there for a second. All right. Now, so that was part A. Because this would not, can anybody tell me, how can you just look at this and tell that it won't have any real answers? Somebody know what to check? to see if it's going to have real answers? Where would complex numbers come from in the quadratic formula? Where can you point to?
Discriminant plus or minus.
The root.
Yeah, the determinant. Discriminant, whatever that was. This piece. What would have to happen to that piece in order for there to be complex answers? Yeah, and what's b squared? 4. Minus 4 times 1 times 2, so 4 minus 8. Totally negative. Cool. Wow. So I know there's going to be complex answers to this piece. You guys with me so far? So there's two things going on here. You got to be real careful. If they say find the factors, then that's a factor. They want you to factor this bad boy. If they say find the roots, I can get -2, and then I can get my 2 complex answers, and I'm done. So if they say factor, if they say find the complete factorization, you actually have to do this. You actually have to give me what the polynomial factors to be. So that's what we're doing. We're trying to factor this bad boy. So if I do quadratic formula, that's going to be the answers. Is that going to be the factors? No, not quite. So how does quadratic formula come out for doing this here? So let's see, 2 plus or minus, we already know that's -4. And what's the square root of -4?
That's right.
Sweet. So this will be 2 plus or minus 2i over 2, so it's 1 plus or minus I. Is that cool? Just cut everything in half? Alright, let's stop there again. Alright, so this answer we got from synthetic division. That's as far as synthetic helps us really, because I can tell that there's no way to factor this using integers. And synthetic actually works for irrational or complex numbers, but I really don't want to. Actually, I do, but we don't want to. So how do I use this? How do I use that to factor this?
You use the 1 plus I.
Plus I and 1 minus I.
That's where you got to be careful. Yeah. So
1 plus I.
X minus
it's never a plus anyway.
X minus 1 minus I, right?
Yeah. How do you build? So why was -2 related to x plus 2? Because you actually build it by doing x minus whatever the 0 is, right? It's always x minus whatever the 0 is. X minus whatever the other 0 is. Always, right? So what do I put in here? You put the zeros. What are the zeros?
1 plus I.
1 plus I.
1 minus I.
So you get x plus 2, x minus 1 minus I. Good. X minus 1 plus I. Wow. That's how you factor that completely. Yes, sir.
So if it says factor over reals, we wouldn't go that far.
No, you'd stop right there. I love it. And you have to know how to check to see if there's a reason to go further or not. Alright, maybe. So building off of what we just did, if I give you a list of roots of zeros for a function, let's say that there's a function g of x, there's a polynomial function that's got zeros of -1, 2, 7, and 5. There's actually multiple answers to this question, but there's a basic answer that I'll accept. What would that look like? Don't make too much out of this. Yeah, it'd be x plus 1, x minus 2, x minus 7, x minus 5. I didn't say anything about multiplicity, so if somebody did that, it'd still be the right answer, right? Because it still has those zeros. I just didn't say anything about multiplicities, but I'm sure most of us would just go, screw that clever crap. We just do that. So if I tell you that, let's say h of x is what's called has real number coefficients. You gotta be careful here, because watch what I'm gonna do. Right? Like this would have real number coefficients, no complex numbers or something pop out, no imaginary numbers, so be careful. Real number coefficients with zeros of -3, 0, and I. So this is going to kind of bring back in something we talked about earlier. The reason that Descartes does what it does at the end. You guys are like, what the hell is he talking about? There's some weird shit that hopefully everybody understands why that happens. But there's something wrong with what I've given you. Not really. I just haven't given you the whole picture. So if you start to write h of x, what would it be?
X
X plus 3.
X. X minus 1 plus I and X minus
X
1
minus
minus
I
I.
squared.
Don't overthink it.
X minus I.
Yeah, x minus I, but in order to be real number coefficients, I just didn't give you the complete list of zeros, right? There also has to be an x plus I. Because how do complex numbers always show up? They show up in
Pairs.
pairs. How do irrationals always show up? Pairs. Why? Because of quadratic formula plus or minus. So there will be some in the homework that say, they give you an I, and if you forget to give its conjugate pair, oh shit, you're going to end up with some weird shit when you try to multiply that back out. You're going to end up with some complex coefficient things. It's supposed to be real coefficients. We don't want to work with polynomials with complex coefficients. Let's not do that. You guys get that idea? It comes right off of that idea. So that one was, we created our own zeros, but then we had to know how to plug it back in. So there will be problems where they just give you zeros. That's even better. I didn't have to do any work. I just got to plug them in. Just be careful if they give you complex zeros. You have to have its conjugate pair there also. Conjugate buddy. Okay. So real quick word about section 3.7. I'm going to just talk about one thing from section 3.7. And then tomorrow we'll finish it off. I don't know if you guys remember, we already talked about this idea before. Something funky happens with this function. And we actually kind of got into it a little bit deep. I don't know if you guys remember this, to see what really happens close to 1. So, of course, 1 is the problem spot, right? The domain would be everything except 1. So something weird has got to happen at 1 visually. It can't just be like a normal thing, because I'm saying weird shit happens at 1. So we looked at it like, let x go to 1 from above. We did 1.1, 1.0, 1, 1.0. You guys remember this? We did the whole thing, and the answers were 1 over 0.1, which is 10, and 1 over 0.01, which is 100. So as it comes, it goes like that. So what is right there? An asymptote. Good. So this is a vertical asymptote. The shields are still up. Pull up.
Independence Day?
Yeah, Independence Day, or it's a trap. Either one. I would accept either one. There you go. Cool. Good. That's what I always think whenever I see one of these things. Oh shit.
That's the quiz that matters. Movie references.
There you go. So where do vertical asymptotes always come from? Okay, good. The denominator would be a little more specific about the denominator. It comes from the domain, as you always say. All the x values you're not allowed to use. Those could be these walls. I call asymptotes walls. Vertical asymptotes are definitely walls. You cannot go through them. You have to come up against them. Horizontal asymptotes, we'll see tomorrow that they're not nearly as wall. You can go through them for a while. Right? We'll see what the hell that's all about. Tomorrow. This is plenty for today. Next class already wants to come in. All right.